Let's continue then with the last part for today, which is advanced value-based methods. That's how we call this, and where I want to introduce actually just two things. I will skip the last part, which is very high level anyways and would take much longer to explain properly. But I highly recommend at the end, and I give you some resources where you can have a look. I will introduce DDPG for deep deterministic policy gradient method, which for some time really was the state-of-the-art method for actor-critic approaches, but also has some drawbacks that I'll mention. And an improved version was TD3. Yeah, we'll get to it later. It introduces some other concepts that stabilize and improve the learning performance, or the convergence of the algorithm, as we'll see. Okay. Okay. First up, deep deterministic policy gradient. So whereas before we took a look at the stochastic policies, right, for the policy gradient methods that we saw. Now we'll talk about actor-critic methods with a deterministic actor, okay? And this DDPG algorithm can be seen as a continuous action space version of DQN, okay? So it basically uses the same overall structure of the algorithm. It uses a Q function approximation with parameters W. It uses target networks. But the main problem is, of course, now that we have continuous actions, the maximization step, of course, in continuous space is non-trivial. Of course, this usually, it could be done with optimization, and it is sometimes done with optimization methods. But that can be costly depending on your problem, of course. And the idea with these actor-critic methods and the the idea behind this policy gradient, deterministic policy gradient theorem, is that you basically want an actor that we call mu that has parameters itself again, theta. We want to train it in a way so that it actually represents the argmax over A for this Q at S J plus 1 A for the given action that we will take, and the parameters W. So we represent this actor by a neural network, and then this deterministic policy gradient theorem actually gives us this update. Yeah. So in the paper, there's a paper by Tim Lillicrap and some other colleagues at DeepMind. Don't remember the exact year, but something like 2017 maybe, roughly. And so there they derived, I mean, the deterministic policy gradient itself was already introduced a bit earlier by David Silver and Martin Riedmüller and colleagues. And in the deep deterministic policy gradient, this is used, but it's also connected with deep neural networks as function approximators, being able to learn end to end from high dimensional pixel inputs, but still using continuous control problems. Okay, so the update, let's take a look. The update, the gradient of, so the gradient of, with respect to our policy parameters theta, is given basically by a combination of, so it's the gradient of the Q function. So that's in the end what we're interested in. How do we need to change our actions in order to get to more Q? Yeah, because Q, of course, is the expected long-term reward, given that we execute an action and then follow the optimal, and then follow the policy. And we want to get to higher and higher Q values, of course. So how do we should we change our actions? That's this part basically. But we evaluated at the action A as given by our parameterized actor. Yeah, so that's this mu part. And so mu, of course, depends directly on the policy parameters theta. So we have the gradient with respect to theta of this mu, the actor, in this given state as J that we sum over here. right? So the policy gives us an action. We take the gradient of that with respect to the policy parameters, and we evaluate our Q function, and we take the gradient with respect to the action A at this particular action here. Yeah, that's the update that we need for our policy parameters theta in order to get to more Q, yeah, to higher Q values. So we do gradient ascent in that gradient. And remember, we're always doing sampling, as always. So we need to maintain exploration. We need to make sure that we keep exploring our environment. And in the case of these continuous actions now, we can't do epsilon greedy or something like that, but we add some Gaussian noise, basically, to the output of our actor network, mu. Right, so as I said, this is an actor critic method. So you have a parameterized representation of your Q function that you fit to an adapted TD target. Yeah, so here you see it. It's again just the immediate reward plus the discounted Q value for the next state, given and for the action as prescribed by the actor. And now you see we introduce target networks both for the critic, yeah, so the Q function, which has parameters W dash for the target networks, and also we introduce target networks for the actor. So we also have a set of parameters theta bar or theta dash. Okay, and just as in DQN, the target networks there, we want to either keep them fixed, or in this case, we want to update them very slowly, yeah, in order to again, come closer to the case of supervised learning, where we don't have this non-stationarity problem that as we change our parameters of a function approximators, also the targets would be changed. Yeah, in order to avoid that, we do this very slow updating of the target networks, both for the actor and the critic. Yeah. Okay. Right. It says here DDPG is very popular and builds the base for more state-of-the-art actor-critic algorithms. So right now, I wouldn't say maybe necessarily that it's very popular. It's still used sometimes, but definitely nowadays other state-of-the-art algorithms that build on DDPG are probably the go-to algorithms by now. And one particular problem with DDPG was especially that it can be quite unstable and sensitive to the chosen hyperparameters. But it can work really well if you have good hyperparameters. That also needs to be said. Okay, so here's the pseudocode. You will see that it looks similar to a DQN, yeah, just as I mentioned before, but there are some important differences, of course. So just as in DQN, we use experience replay, we store everything in our replay memory that has a finite capacity, and we just initialize the parameters for actor and critic, and then for the different episodes, we loop through the steps of the episodes. We select the action AT for the current time step according to what the actor says we should do in state ST, yeah, with our current parameters theta, and we add some normally distributed noise to it to maintain the exploration, right? So this is just zero mean noise with a fixed standard deviation here. We store the tuple of state action, next state, and reward in our replay buffer. And then we can sample a mini batch of these transitions from the replay buffer, and we calculate our targets, yj. Again, if it's a terminal state, we'll just take the immediate reward. And if in every other case, we calculate our target using our target networks, yeah, for both the actor and the critic. We will update the parameters of our critic, Q, the Q function, according to the TD error, and we update the parameters of the actor mu according to this deterministic policy gradient theorem update. Yeah. So again, the update the gradient of the actor with respect to, or rather the gradient of the Q function with respect to the action, evaluated at the action that the critic would give us in the state, multiplied with the gradient of the actor with respect to its parameters for the given state. And we adjust the parameters of the target networks as well, given the soft update that you saw on the slide before. Okay. Yeah, before I go on, maybe I'll see if there's some questions up to here. Continue. Okay, so one particular problem that we tend to have when we basically always when we have a Q function and we have wrong initial values with a function approximator especially, but it's basically that if we then take a maximum of some noisy estimate, we tend to use those estimates that have the highest noise value. Okay, so the noise can create a problem in connection with the maximum and can sometimes lead us to be overly optimistic, if you like. Yeah, so sometimes we overestimate the Q value due to some noise. That's due to the stochastic estimation. And if we do this repeatedly, then that can lead to really being overconfident with respect to our Q values. Yeah, so we saw that we always use this maximization of the value function. Right, so we take a maximum of the estimated values. Yeah, we use it as an estimate of the maximum of this value. Yeah, so we pretend that that's the right maximum value, but it includes some noise. Yeah, so that really can lead to this overestimation bias, and it's maybe easiest to see with an example, yeah, of this very simple little MDP that we have here, just two states, A and B, and from A we can either go right with a reward of 0 or left with a reward of 0. And then from state B, we always transition to this state on the left here. If we go right, we also transition to a terminal state, but with reward 0. And here we first transition to B, and then we transition automatically to this terminal state, but with a stochastic transition. And the stochastic transition will give us a reward that is coming from a normal distribution with a mean of minus 0.1 and a variance of 1. So intuitively, if we look at that, it should be worse in expectation to go to the left, right? Because if we go right, we always get 0 deterministically, and on the left, in expectation, we will get a reward value of minus 0.1, so it's worse, right? Okay, so however, what happens? Do I have? Yeah. So what happens? Maybe I just go here and then I go back. What happens if we apply Q-learning is that if we look at the percentage of left actions, the worst action, from the state A, when we apply Q-learning to this little MDP, is that at first, the Q-learning will rapidly increase the percentage of left actions chosen from this state, because it gets overconfident. It gets these noisy transitions, and it will always take the max. Yeah, it will always consider the mean value plus the noise, of course, that's coming from this distribution, and it will think, hey, this is the better choice, so I should go with the left action, right? And it will increase that up to a certain point, when then actually you have enough samples to be able to more reliably estimate the mean. And then at some point, it switches over. Yeah, so then you get to less than 50%. But this initial rise is due to this overestimation effect, and it's something that's of course slowing down learning. Yeah, so we will now what follows, we'll introduce the double Q learning, which addresses this effect of overestimation bias, and you can see that it much more quickly comes to something very close to the optimal Q values. Yeah. Okay. Yeah. Sample 5%. Good question. I would think now that this is maybe because you're doing optimal. I mean, yeah. I mean, in order to maintain exploration, you should actually sample some suboptimal values. Yeah, that would be probably an explanation, that you maintain some exploration by epsilon greedy. But that's the lowest you could get then, I guess. Yeah. That's my only explanation. I don't remember exactly, to be honest. But yeah, otherwise it would be weird. So otherwise you would the optimal, without having to care about exploration anymore, would have to be 0, because you don't want any negative samples, right? I think. Okay. Right. So if we take a look again at the Q learning target, yeah, that was the immediate reward plus the discounted max over A of the Q at the next state. Yeah, so that's the Q target in general. And in general, it's not perfect. Our Q values are usually not perfect, because we have to initialize them with some wrong values. We are biased, and then also we update them with stochastic approximation. Yeah, so there is noise in the update, definitely. And now, for now, just let's consider to abstract random variables x1 and x2. Yeah, then it is true actually that, if we take the expectation after we take the max of the two, yeah, that's not the same as taking the max when we first take the expectation of both. Yeah, so taking the expectation of the max of the two will always be greater or equal to first taking the expectation and then performing the max. Okay, yeah, I think this can be shown with Jensen's inequality, but yeah. I don't remember exactly, but I think this is where this comes from. So the expectation, if you first take the max, then of course you consider the noise, right? You have noisy samples, you take the max with respect to this noise that you have, and then afterwards, then you have already chosen, so to speak, which one will be your max, and then you take the expectation. But then you take the expectation for that for the sample that has the higher noise. And if you first take the expectation, you would average out, so to speak, the noise, and then take the max. Yeah? So in any case, this Q is not perfect. It contains noise, and then here, you say that, well, in order to compute the max over actions for the Q at st+1, what you do is you take the Q value for that state, and you put in the argmax of this Q function. And the problem is now the action. So both of these come from Q. Yeah. So the Q itself you evaluate, and also the argmax is evaluated using the same Q function. So both of these things, yeah, the Q here and the Q here, are affected by the same noise. Okay, and that means that the noise is correlated. Yeah, it's directly correlated, because you take the same Q function. If we were able to decorrelate, using two different Q functions, then we would have decorrelated noise, and then we wouldn't have this problem that we maximize, we take the value of 1 and we maximize with the same Q function, then because then, you know, the noise would be in different directions potentially. It wouldn't always be in the same direction. So that's basically what this algorithm tries to do, which is called double Q learning. So in double Q, you basically introduce two Q functions. That's why it's called double Q, Q1 and Q2. And yeah, you basically, in this version of the algorithm, you update either one of them at each step of the episode, and you just flip a coin basically. So with probability 0.5, you either update Q1 or you update Q2. And in the update of Q1, as you see, of course, you use your old value, but then, you know, for the evaluation of the target itself, you use Q2 here. Yeah, that has different initial values and is updated different number of times. And for, you know, calculating the argmax, you again use Q1. Yeah, and here also use Q1. But, you know, because you update them differently and you initialize them differently, they will have a different amount of noise that are introduced in their updates. Yeah, in that sense, they then will be decorrelated. It will not be the same, exact same updates and exact same initial values that lead to the noise in these values. And by doing that, you decorrelate the noise, and then you have this problem much less. Yeah, so you can, for these kinds of problems, you can have a much quicker convergence. And this is really the basis for a still state-of-the-art algorithm that's called TD3, which introduces three extensions or improvements over DDPG. A version of the double Q learning that we talked about, delayed policy updates, so it will update the policy slower than it will update the critic. And it also introduces another kind of smoothing, which adds some noise on the targets in order to basically regularize the targets a little bit more. And that can lead to more stable learning. So let's take a look at these different improvements here. So clipped double Q learning. So, you know, as we talked about just a few minutes ago, having double Q learning or two Q functions, two different versions of a Q function can, if we use that in order to calculate our targets, then that can bring down this overestimation bias. And here, the way this is implemented is that it takes a minimum of, so it basically, it takes the minimum of both predictions as the second part of the TD target. So it will have, again, you know, two versions of these parameters for the Q function. So you have W1 and W2 for the target nets, and then you take the minimum Q value either for this W1 or W2 bar. Yeah, if you update this, and then you update these two Q functions again. It's in different ways. Yeah, so you don't have the same update always. So this is the way that you implement this in TD3, and this can lead to better convergence, as we can see. So the let's see, the true DDPG version is. I'm trying to figure out what was this. So the So DDPG basically overestimates, like we see here. So the average value that it outputs in its Q values would be higher, but the true values would be this orange curve here, and you can see that. For the blue objective, this is this clipped double Q learning that's in TD3. Also, so this blue line and this this dotted blue line, they're much closer together. So here we actually have more like an underestimation effect. So it's much more careful not to overestimate if you compare it to DDPG. Yeah. Okay, the same you can see here, right? So for the orange curve, the smooth orange curve is much higher than the true one, which is this dotted line here. And for the clipped double Q objective, they match very well. Yeah, so this is actually following the real values much better. Right, then we have delayed policy updates. Yeah, and so basically the explanation here is we have this mutual dependency between actor and critic updates. Yeah, so the actor depends on the actions that the critic takes. Sorry, the critic depends on the actions that the actor takes, and the critic in turn is used to update the parameters of the actor. And still we can have, you know, divergent behavior when we still have some kind of overestimation effect. And sometimes the policy will lead us to bad regions of our state action space if the value estimates are just not good. Yeah, if we use that then for bootstrapping in the updates for the policy parameters, that can lead us to bad regions that we maybe don't want to get to. That will also slow down the learning process. Yeah, so basically then the policy updates on these states that have high prediction error, they can sometimes still lead to divergent behavior. The thing is, we already introduced target networks, yeah, for the critic in the QN, and also here in DDP in the TD3 we use that, but we now want to decouple this even more. Yeah, so we basically want to decouple the updates of the critic even more from the actor. And what is done here in TD3 is that we make the updates for the policy parameters even slower than for the critic parameters. Yeah. So we freeze the target and the policy networks between, for instance, d-updates of the value function. So we make d-updates to the value function, and only then we update the parameters for the policy. Yeah, so that's the delayed policy update, and it can help to you know, break to some degree the mutual dependence between actor and critic. And finally, target policy smoothing. That you know, that helps to stabilize things a little bit more even. So it's a regularization that you do here basically. So you add Gaussian noise when you calculate your targets, yeah, your update targets. And so we didn't talk about expected SARSA. There was a question before about expected SARSA, but it's a little bit similar to those of you who know about expected SARSA in the sense that we consider, you know, not just the Q values directly, but also a little bit around them, if you like, since we add this, you know, when we calculate the Q values, we don't just use the value of the actor directly, but we add a little bit of noise to it, which means we look a little bit around the actual action that the actor would prescribe for the given state. Yeah, and that can actually make things a little bit more stable. Okay, but it's clipped noise that we add here. Good, and I mean, these were things that were figured out and were combined in this TD3 algorithm. And now they did an ablation study where they compared the full TD3 method, of course, to DDPG that it's based on, and also yeah, so this AHE was architecture, hyperparameters, and exploration. Sorry, I don't remember this AHE, but in any case, you can see the difference if we, first of all, of TD3 over just DDPG, and it's quite a bit better in many of these continuous control tasks in the Mojoko simulator or in OpenAI Gym using it. And then they looked at, well, what happens if we just use delayed policy updates? what happens when we use this target policy smoothing and this clipped double Q learning. And you see that it helps, yeah, over just using DDPG, but the best is, of course, if you combine all three of them. Okay, and I think we'll stop here. Yeah, let me see if there's some questions, and I won't go through the soft actor critic. This is, of course, a state-of-the-art algorithm at the moment, so I recommend to read the paper on it. But you can also read more about it here at this very nice web page from OpenAI. This is called Spinning Up RL, and this has a lot of nice tutorial-style information on these state-of-the-art algorithms, and also some code examples that you can look into. Yeah. So thank you, and let me know if you have any questions that we can discuss before we go to the exercise.